Yeah, comes on everyone. Let's start off. Great. So last thing we did was this barometer.
So the homework question also comes.
What was the homework question?
That
Yeah, to send me the
volume.
working. No? You send me the working. I'll tell you whether you got it right or not.
So right now, like after class.
Send it whenever you can. I'll see.
Okay, so
Let's see. Other scams on. Great. The next thing is ban force. So what is this ban force? So when a body is immersed in a fluid, it experiences an upward thrust. Equal to weight of the liquid displaced. Getting it? Now this thing is completely experimental. So you must have heard the story, right? The Archimedes ka Eureka thing. So you know what is Archimedes famous for? What? What is he famous for? Shouting Eureka, Eureka on roads. He's famous for making weapons. He's actually a getting it. During that time, Greece, mein, they used to have these five cities: Athens, Greeks, these Spartans, all these people. Some more cities are there. So during that time, there is no PUBG, Instagram, nothing. So people are bored. So what they do, like, yeah, bore kar rahe, kya kar, let's attack. Meaning these people just used to wage wars. Happens when you're bored. What you do, you fight wars. So Athens on the other side, right, is like a weak city. It is not a strong one. And Archimedes used to stay there. This guy is famous for making a lot of weapons. One weapon he made was a death ray. Death ray is nothing but a concave mirror. So they used to focus the sun ka light rays and used to shine that on a ship ka sails. So when the enemies used to attack, right, they used to shine this concave mirror ka thing on that. Now because of this, what will happen? The focus sun light rays, the ships used to catch fire. Not a big fire, but the sail used to catch fire. Now before doing this, you spread rumors that the city of Athens is protected by the sun god Apollo. So now you start spreading so much rumors, right? If you get close to the city, sun god will burn you. You are like, kuch nahi hoga aisa kuch. And then you start attacking the city, and suddenly your ship catches fire without a reason. You're getting it? So people used to be shit scared, like, oh shit, Randy, seriously, sun god is protecting. Let's not attack. That's a death ray. He's famous for making catapults. He used to create all kind of weapons for the king, and that is the reason king was so impressed with him. So he used to get all the funding for that. He used to say, like, king used to say, do whatever you want, just make sure you're making enough weapons for the country. And another weapon he has was hell's fire. This guy found an oil deposit somewhere and he used to use catapults and throw this thing onto the ships. Now normally when there's a fire on a ship, you think about it. What is the first thing you do? You take water and throw on it. But if it is an oil ka fire, what happens? The oil floats, the fire doesn't stop. That's why it is called hell ka fire. It never stops burning. Right? And you spread one more rumor. The god of underground, or this underground god or whatever, Hades, is protecting the city. So daytime Apollo protects, nighttime Hades protects. You create enough rumors and you scare the people not attacking the city. The story goes on like that. So one fine day, the king gets a nice crown, gives some gold to a goldsmith, and tells him to make a crown. The goldsmith makes a beautiful crown, and the king likes it. But somewhere, king gets suspicious. Did this guy steal some gold from this crown? And this guy wants to find out how much gold is there in the crown. One way to do is what? You burn the, you melt the crown. You'll find out how much gold is there, how much copper is there. But the problem, crown will be destroyed. Now, Archimedes is there free, ना क्या कर रहे हैं उसको तो funding दे रहे हैं, call him up and then say like Archimedes देखो ये मेरा problem है, I have a beautiful crown, do something without destroying and find out how much gold and how much copper is there. That's what happens when your sponsors are there. That's what they do to you. They have something and they expect you to solve their problems. So this guy goes to a public bath, sitting in a water, thinking, and you must have felt this, when you're inside of water, you feel little weightlessness. And something struck him. And that is when he started shouting, Eureka, means I found it, correct. The story goes like that. Now, what did this guy exactly find? Let's see that. Now, the reason why we give so much importance to Archimedes, right? This guy figured out this buoyant force and all that stuff 2000 years back, even when we didn't have a concept of forces and pressures and stuff. Now, if you ask Archimedes why, he will say, I have no idea, but every experiment that I did proves there is something called buoyant force. So Archimedes has no clue what it is. But let's see what does this. It's more of an intuitive thing. So consider we have a container of liquid. Now, inside the liquid, imagine a cube. It's not there. Just imagine a cube. Now, in this cube, the liquid amount of liquid is constant. It is imaginary. You are just imagining it. So if the amount of liquid is constant, the mass is constant. Now, if you draw the FBD of this, now this is what Archimedes says. He says the cube has some weight, which is density of the liquid, volume of the cube into G. Any body. Now, if you have a weight pulling down, shouldn't the cube fall down? The cube should fall down, but for some reason, the cube is not falling down. That means someone must be balancing it. Now, seeing here, who can balance this cube? The surrounding liquid. There's no one else, isn't it? So he said the surrounding liquid is exerting a force which is balancing the weight of the liquid. And if you ask him here, how is this happening? He says, see, boss, I have no clue. Why is the surrounding liquid pushing it? But from the intuition that I can see, the weight is pulling down. Someone has to balance it. And I can't see anyone there except the surrounding liquid. Is that making sense? It's like you and your sister are in the house, right? Your mom kept two chocolates in the fridge. Both are vanished. You didn't eat. Who has eaten it? There's no proof. There is no video recording that your sister ate it. But conclusively, there is only one answer, isn't it? Getting it? This is a proof without a proof. There are two chocolates in the fridge. You didn't eat, but both the chocolates vanished by evening. Only you and your sister are in the house. Right? Now, isn't that what happens? Getting it? So, so this guy said this surrounding liquid force is what we call as buoyant force. This is buoyant force. Now, the imaginary cube of liquid must be balanced by force due to surrounding liquid since it is in equilibrium. Now, if we replace this cube, now this is what Archimedes says. Now, if I replace this with a solid. The FBD becomes density of the body, volume G. Now the surrounding liquid will still exert the same force. See, surrounding liquid doesn't care what material it is, which is something but rho LVG, isn't it? So the place of the liquid which you have removed, the surrounding liquid will continue to exert the same force irrespective of what material it is. Because it only depends on the surface area and everything, isn't it? So if density of liquid is greater than density of body, the body floats. If density of the liquid is less than density of the body, it sinks. So whether a body sinks in a liquid or floats in a liquid doesn't depend on its mass. It depends on the density. So if you take a fit person and if you take a fat person and throw them in the water, who will float better? The fat guy. Because a fit person will have more muscle and muscle has more density. A fat person will have more fat. Fat has less density than water. If you see, elephants are pretty good swimmers. Elephants actually, if you throw an elephant into water, it floats. But and if you throw a rat into water, it actually sinks. Rat will drown, even though the mass is less. So what decides whether something is floating or sinking is not the mass or the weight, but the density. Same reason, right? Ships are so heavy, but they float. Reason the average density of the iron plus the air inside the ship, the average density is less than the water car density. That's the reason ships float. So if you throw someone into the water, they sink and die. After they die, they float. You know why? If you take when the person is alive, they're struggling and everything, they die, they fall into the water and they sink. After they die, the body floats. So if you kill someone and if you're trying to dispose the body, throwing into a lake is a very bad idea. Which you're not supposed to kill anyway in the first place. But why do you think the body floats? Because body ka atma goes off, weight reduces, and the body floats. Ne? Looks pretty logical. Ne? Once the atma leaves the body, density of the body decreases. What do you guys think? Any guesses? Why a person alive, right? If a living thing, if you put it in the water, it sinks. But once it is dead, it actually floats. It should have been reversed, na? Blood vessels, well, yeah, no. Blood vessels has nothing to do with floating. Any other guesses? I know you have not killed anyone before and kept them in a lake, but can you guess? Body gets inflated, lungs are full of air. Arey boss, God, he died. How the hell he get will air in the lungs? Dead bodies don't breathe, unfortunately. What happens, right? Once the body dies, it decomposes. So once the body starts decomposing, it starts releasing methane gas and all that stuff. So if you see the body actually bulges, it gets inflated. So the tummy starts accumulating all gases and the body floats. One of the reason, if a whale or a big fish dies and comes to the shore, you're not supposed to go and touch it and poke it. If there's a big whale dead and gets washed off onto the shore and it is there, mostly it is decaying inside and it is releasing a lot of gas. A lot of gas. It's like a bomb sitting there. You go there and poke it, there's a high chance it'll explode. So if there's a dead whale, a big one on the shore, better you leave it. Normally what people do, they put dynamite and blast it actually. Just to make sure. So next thing. So what is this buoyant force exactly? Now, if you ask Archimedes, why is buoyant force coming? He will say, boss, I have no idea. But experimentally, this thing is true. So the reason why buoyant force is coming it is due to the difference in pressure between upper and lower surfaces. So be careful here. If you use the word bind force, don't talk about pressure. If you talk about pressure, don't talk about bind force. Both are one and the same thing. In an FBD, either use bind force or pressure, but not both at the same time. It is like, centripetal acceleration and centrifugal force. You can't use both of them, right? Both are one and the same, depends on the frame. So bind force is an experimental quantity, whereas the FBD forces and all is actually theoretical. Force or pressure, but not both at same time. Simple reason is bind force is an experimental quantity, whereas pressure is theoretical. You're talking about the same thing in two different languages, basically. So Archimedes didn't have an idea like why it is coming, but he knows it is working. So if you see certain properties here, bind force is always upward. I hope you remember what is up and down. What is up and down?
Direction of net force.
Yeah. So upward is opposite to direction of net force. So if someone asks you to find the bind force, it will be density of the liquid, volume displaced, into G effective. So you can take effective gravity, G plus A, G minus A, all that stuff if the system is accelerating. Third one. This is an important point. Huh? This could be a good question, actually. We'll see later on. Force due to liquid and bind force need not be same. Most will get confused between these two. They think it is the same thing. I'll show you how it means. Force due to liquid and bind force. Have a look at this point. Clear? Next one. So where does this bind force exactly act? Bind force acts on the center of mass of the displaced liquid. That means let's say you put a rod in a liquid and it is floating like this partially. The weight mg will act on the center of mass of the rod. But whereas the bind force, if you see, this part is displaced inside. So this point is center of mass, the bind force will act here. This is the center of mass of displaced liquid. So the rod has displaced that liquid, it will be on the center mass of that part. So be careful with that. Bind force will not act on the center mass of the system. We can also call this thing center of buoyancy. So for example, let's say if you take a cylinder like this, x is equal to 0, x is equal to L, and let's say lambda is equal to lambda naught x. And if I dip this inside a liquid, can you tell me how will the forces be? They can ask a question like this: find the angular acceleration of the rod. What will be the forces? And let's say area of cross section is there. Where is the center mass of this rod? Lambda naught x. We have done this in center of mass. It will be at x is equal to 2L/3, if you remember. So the weight mg will act here, whereas the bind force will act here. Isn't it? So how will the rod rotate? Clockwise or anti-clockwise? Rod rotates about the center of mass, so it will rotate clockwise. Clear? Questions can be framed like that. Every time the bind force won't act at the center mass of the system, it will act on the center mass of the liquid. So if you put a non-uniform rod, the liquid doesn't care whether the rod is uniform or non-uniform, because what you displace will be uniform liquid. I hope that is making sense. Have a look at this. So these are some of the points. Bind force is always upward. Second point, if you apply bind force, don't talk about pressure, or if you talk about pressure, don't talk about bind force. Third, force due to liquid and bind force are need not be the same. Clear? There is not exactly a point, but you can write down this. You can't use bind force if the total lower part is not covered by the liquid. For example, let's say there is a hole like this. If you see here, this is atmosphere. If entire lower surface is not covered in same liquid. Better use pressure method in these cases. So bind force is pretty useful for irregular shapes. Just have a look at this. Let's see. Let's say a question on this that will make things clear. So we have a container.
Sir, can you go to the previous page for 1 second?
Hmm.
Oh, sir, thank you.
Density of liquid is rho L. There is a cube here. Of side L, and density of the block is rho B. Rho L is the density of the liquid. So this part here is submerged inside the liquid. X is the length submerged inside the liquid. Outside pressure is atmosphere pressure, P naught is there. First question, find X. Find force due to liquid. If container is accelerated up, down, and horizontally with A, 3 different cases. Find a new X. Meaning accelerate up, accelerate down, and accelerate horizontally. Get them. Take a minute, then I'll show you. Rho, begin rho. Okay, let's see.
We would need the length of object.
If you read the question, you will see. Did you find? On the top left. It's a cube of side L. Let me show you this in 2 ways. First things, this is important, listen. Let me use bind force. So this part of the liquid was immersed inside. This was X, this was L, and this was also L. So if you write the forces, the bind force will be density of the liquid, X, L square volume displaced into G. Your own weight mg, which is rho b volume L cube into G. Bind force is equal to mg rho L x L square G is equal to rho b L cube G. X is equal to density of the body by density of the liquid into L. Now the same thing, if I use the force method or if I use pressures, so from the top, the atmosphere is pushing down with P naught into L square. At the bottom, the pressure is P naught plus rho liquid G X into L square. This is the force due to liquid. Hope you're getting the difference. This is not buoyant force. If they ask you find the force due to liquid, it is pressure into area. Getting it? And your own weight mg. Now, if you write the difference here, P naught plus rho liquid Gx L square minus P naught L square is mg. So this whole term is buoyant force. This is what I was saying. Buoyant force is nothing but the difference in force between upper and the lower surfaces. So if they ask you find the buoyant force, this is the answer. Weight of the liquid displaced. If they ask you the force due to liquid, it is something else. And if you solve this, you get the same answer. X is equal to rho b L by rho L. Answer will come same. The difference, it is like, think of like this. Let's say person A is there, person B is there, and there is some charity here. You're supposed to give some money. A gave 100 rupees to B, and B added 50 rupees, and he gave 150 rupees to the charity. Now, if you ask Archimedes, how much did A donate? He will say 100. How much did B donate? He will say 50. But if you ask Newton's laws of motion, FBD, right, he will say what? A has donated 0, B has donated 150. Because in an FBD, what do you draw? You always draw the direct forces. You don't care about the indirect forces. If I take a book and hit you, who is hitting you? The book. The problem with the force method is we always take the direct forces. We don't care about the other contribution. Are you getting the difference? Force due to liquid is something else. Buoyant force is something else. Let me give you one more on this, but have a look at this first. What else did I ask you? If the container is accelerated up or down horizontally with A, find X. That's your third question.
Sir, can you show the question for a minute?
Hmm.
Yes, sir. Thank you.
What is the answer? Same story. If you look at the forces, Now the bind force will be rho liquid volume displaced XL square. This will be G effective. And this will be mg effective. Since it is in equilibrium, FB is equal to mg effective. G effective will always cancel. Answer is independent of acceleration. Whether you go up or down, right? The only difference is the horizontal one looks interesting. If you accelerate horizontally, the only difference will be liquid will become like this. So the block will become like this. So the X will still remain same because X is the liquid depth inside of the liquid. That doesn't change. You're getting this? Whether you accelerate up, down, or right, left, doesn't matter. That X is the depth inside the liquid will remain same. This is independent of acceleration. Simple reason, this force is 10, this force is 10. If you double this and if you double this, it will still be in equilibrium, isn't it? G effective is getting multiplied on both the sides. Independent of acceleration of container. Because the question is weight of the liquid displaced. So weight of the liquid displaced also will increase. The weight of the block also will increase by the same factor. Clear with this? Now, this question, I can make it even one more level. Suppose the same thing. This time you seal the container. Container is sealed and air is pumped inside, doubling the pressure. The pressure inside becomes 2p naught now. Now what will happen to X? Will it increase, decrease, or remain same? Is the question clear? If you seal the container and if you pump air inside and you make the pressure 2p naught instead of p naught. Now what will happen is find the new X. X is the depth of the block is one inside the liquid. It doesn't matter. Remember Pascal's law? If you increase pressure at one point, it increases everywhere. So if you draw the FBD, this will become 2p naught into L square. This will become 2p naught plus rho liquid GXL square. The 2p naught term will always cancel. Temperature is constant. Temperature is constant. So you get the same thing, rho B L by rho liquid. So basically pressure increases everywhere, Pascal's law. If you try to push more from the top, you're pushing more from the bottom also. Clear? Any doubts on this? So accelerating the container won't affect the X. Increasing the pressure won't affect the X. Any doubts on this? Clear, na? Abhinav, Adrit? Aditya, got this? Utsa, Palaksh? Next one. Let's say we have a long container. Let's say this liquid is ρ1. This height is h1. This liquid is ρ2. This height is h2. This liquid is ρ3. And inside this, you kept a cylinder. Area of cross section is A. And this height is h3. Exactly till here. Outside the pressure is P naught. Okay. Find force and bind force due to each liquid. Find force and bind force due to each liquid. Total 6 answers will come up. There are 3 liquids, you'll get 3 forces and 3 bind forces.
So it's not completely submerged, right?
Yeah, it is the diagram what I showed you is that only. Is my diagram looking weird? You're not able to comprehend my artistic skills. You should comprehend by now. Get it. There are 3 liquids, ρ1, ρ2, ρ3. And you kept a cylinder inside. Cylinder ka mass and all, I don't care about that. I just want force and the bind force due to the liquids. Bus. I hope the question is clear. Anyone confused, please ask. Get them. You got 2 minutes. It's a good one. So most people get confused between bind force and force due to liquid. That is the whole point of this question. Because exam they'll ask you in a paragraph question, force due to liquid. People will write bind force and come.
So we don't have the density of the cylinder either, right?
Why? Why do you need it? Chalo, take it as rho B and show me where you needed it.
No, acha, oh, it's not.
Show you. Try it, I'll give a minute more. Let's see. So if you actually draw the FBD of this, you will notice this red liquid, right, is pushing like this. The force is actually acting horizontally, isn't it? and they all cancel out. The green one is pushing like this. There also, so green is also actually pushing horizontally. Green is not pushing up and down. That also will cancel out. The blue is pushing like this, and it is also pushing up. If someone is pushing the whole thing, it is actually the blue liquid which is pushing it up. So if I ask you the bind forces, so the liquid 1, the value is density of the liquid, area, volume into G. Bind force due to the liquid 2, let me just call it FP1. Because bind force is simply weight of the liquid displaced. Rho 2, area, H2, G. The bind force due to liquid 3 is rho 3, A, H3, G. But if you want force due to liquids, F1 is 0, F2 is 0, F3 is P0 plus rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3 into area. You literally have to take the pressure at this bottom here, and so pressure at that point is P0 plus rho 1 GH1. That's what I said. If I ask you force, you have to take the direct forces. Buoyancy force is an effect of direct and indirect forces. Now you might be asking, like, sir, if B1 and F1 and F2 are not pushing, why are they getting buoyant force? Listen, logically. Suppose if rho 1 liquid was not there, won't this term be missing from here? If the red liquid was missing, won't the pressure term from here, rho 1 GH1 term won't be missing here, isn't it? That means indirectly, because of the red liquid here, the pressure at the bottom is increased, and that is indirectly pushing it up. I hope you're getting the reason. The red one and the green one are actually helping to push it up, but indirectly. But laws of motion, right? FBD, what it says, I don't care about indirect forces. I will only draw the direct forces. Whereas bind force, Archimedes thing, is more of a practical thing. It will say, I will take the effect of direct and indirect forces. So this is a contribution of the red liquid to push it up. Whereas in reality, if you look at in terms of forces, red liquid is not doing anything. I hope you're getting the difference between force due to liquid and bind force due to liquid. It's like your mom gave you 100 rupees and she told to give 50 rupees to your sister. Happens, na? Grandma and grandfather, when they go, they give you some money. They give you 100 rupees and they'll say share between you and your sister. So you're supposed to give 50 rupees to your sister and 50 rupees to this thing. But you will behave as if the 100 rupees is yours. And you will talk to your sister as if you're donating your 50 rupees. And for that, they have to be grateful. You expect that, isn't it? But in reality, that is not your money only in the first place. So it is like that. Everyone knows the grandma gave the money. But that directly you got it from your sister or brother. I know, you guys 50 rupees kuch nahi hai. You guys take 500,000 rupees, I suppose. You guys are a little expensive. Clear with this? I hope everyone got with the force due to liquid and bind force due to liquid. When we were in school, we used to get 5 rupees. It was a good money, but still. Everyone clear with this? Rehan, Lakshika, got this? Anika, Vartika, clear? Palaksh, Udayan. Next one. So be careful. Force due to liquid and bind force due to liquid are two different things. This question, I hope it makes clear. Container, we got a cube. Side L. Alpha is the coefficient of linear expansion of the cube. Density of liquid is rho L. Gamma is the coefficient of volume expansion of the liquid. density of the liquid is greater than density of the body. It's floating basically. So the question is find a new x when temperature changes by delta T. So when you change the temperature, the body will expand, the liquid will expand, density will change, everything gets messed up. Thermal expansion, fluid mechanics. Alpha is the linear expansion of the cube. Gamma is the volume expansion of liquid. And you know this thing, whenever you increase the temperature, cube will expand, liquid will expand, the liquid density will drop. The bind force gets messed up.
So just for 1 second, can you show the previous answer? Yeah, thank you.
21. Anyone not clear with the question, please ask. They can ask you like this also. Find a relation between gamma and alpha if x remains same. We'll figure it out. First thing, what will happen to the cube? Let this be y. This will be L into 1 plus alpha delta T. This also will be L into 1 plus alpha delta T. So the bind force will be density of the liquid, which is rho L into 1 plus gamma delta T. Isn't it? That is a liquid new density. Rho naught by 1 plus gamma delta T. In case you forgot, you have to go back to thermal expansion because mass remains constant and volume increases by this amount. Into this guy will be y into L square 1 plus 2 alpha delta T. Binomial approximation we can use into G. Whereas when you increase the temperature, what remains same? Mg remains same, na? Mass does not change. Mass will be simply rho b L cube into G. Now, if someone says, sir, body ka density bhi change hoga, this is what is actually happening. Body ka density will be rho b into 1 plus 3 alpha delta T. But body ka volume is L cube into 1 plus 3 alpha delta T, which will cancel out anyway, which is rho b L cube. Body ka mass won't change because you change the temperature. Now equate them. Rho liquid y L square 1 plus 2 alpha delta T by 1 plus gamma delta T G. M will be rho b L cube G. So we get y is equal to rho b L by rho liquid 1 plus gamma delta T by 1 plus 2 alpha delta T. That is nothing but the old x. You can use binomial approximation 1 minus gamma minus 2 alpha delta T. So if gamma is equal to 2 alpha, x remains same. Check it out. This is that old x. Clear? Next one. This is a liquid density rho, and this liquid is 4 rho. And you immersed a block here of density 2 rho. So it cannot float because it is denser than rho. It cannot sink because it's lighter than 4 rho. It's a cube. Find x. Yeah, get it. This is an easy one. Yeah, density of the cube is 2 rho. L by 3. See. So there'll be two bind forces. If this is X, this is L minus X. So upper bind force will be rho L minus X L square G 4 rho X L square G and your own weight mg.
Sir, F1 का direction ऊपर होगा.
Bind force is always upward.
Oh, right. Okay.
Why are you writing forces? Then don't talk about bind force, na? If you want to write pressure. In this case, what she's saying, the force due to the upper liquid is actually down, isn't it? Force due to liquid is down, but bind force is always upward. Don't mix it up. Be careful. These are bind forces. Basically, all this liquid ka weight has increased the pressure here, and that is pushing more than what it is pushing down. FP1 plus FP2 is mg. You'll get X is equal to L by 3, L by 3. Check it out.
So the upper liquid is not displacing any of the down, like the lower
It
liquid.
did displace, na? In this place, what liquid was there before? That L minus X was what? This was all rho liquid, isn't it?
Acha.
Sir, if I was to
Hmm.
use the pressure wala method, then
Use now. Then let this height be h. वैसे start करो. P naught plus rho g h plus rho g L minus x plus 4 rho g x into L square. वो सब pressure निकालना पड़ेगा in terms of h. They'll cancel out, but you'll get the answer.
Okay.
Clear? So let's say we have a cone here. Basically, this cone is blocking the liquid का flow from here. Let this height be h. Diameter is 2r. And let's take the cone ka height is also h. I hope you're getting the middle part. That is a cone ka cross section basically. We don't need to draw that anyways, but okay. So the question is, liquid density is rho and outside pressure is P naught. Find force due to liquid. First one on the cone, net force. Second one, force on the upper half, force on the curved part of upper half. So on curved surface upper half, basically this force I'm asking. Let's call it F1. This I'm asking. Find force on the curved surface on the upper half, which is F1, and lower half F2. Let's get this thing. So this cone is immersed inside a liquid. It's at a depth h. The height is 2r. This is also h. Outside, this is also P naught here, exposed to atmosphere. So basically, it is blocking a hole. Find the force by the liquid on the cone. Just give it a try. Let's see. I think you might need a little more data, I guess. Blocker density. You need blocker density also. Take it as rho b. System is at rest. P naught pi r square by 2. Seriously. See, there are two things happening here. When you took the cone this way, there are two forces on the liquid. There is two forces here. They're pushing this way. They're pushing this way. So remember, this will generate a horizontal force Fx, which is pressure at center of mass of projected area. In this case, this is your center of mass for the projected area. into the projected area. So this depth height was already h, and this was r. So the horizontal component will be p naught plus rho g h plus r into pi r square. This is the horizontal component. And if you look at the vertical components, this guy would be f1 ka perpendicular component, or let me write it as f1 ka y component, and this is f2 ka y component. You're getting, each force will actually have two components. If you look at this thing now, this has two components. This is f1 ka horizontal component. This is f1 ka vertical component. This guy will also have two components because the force is acting at an angle, right? This will be f2 ka vertical component, and this is f2 ka horizontal component. So this resultant force is nothing but f1x plus f2x. Are you getting it? The curved surfaces are pushing it horizontally also, and they're pushing it vertically also. And what are these vertical forces doing? They're balancing the weight. So f2 vertical minus f1 vertical is nothing but mg. Isn't it? Because it is an equilibrium. Or even better, this is nothing but the bind force. Isn't that the definition of bind force? The difference in force between the lower and the upper surfaces is called bind force, which is nothing but density of the liquid into volume of the body 1/3 pi r square h into g. I think that is better. You don't need actually this density of the body. Or you might need. We'll see. But have a look at this. That's the definition of the bind force. The difference in pressure between the lower and the upper surfaces generates a force. Now you need to find f1x separately, f1y separately, f2x separately, f2y separately. Isn't it? The question is find f1 and f2 now. How to find x and f2x separately? Any ideas? Please have a look at this page first of all. Is this clear? To find f1x separately, look at this. You just take the upper half of the cone.
Projected area से कर सकते हैं.
Yeah, how to find the pressure? Remember pressure at the center of mass ना?
Yeah.
इसका center mass कहीं पे होगा? 4r/3 pi. Isn't it? So this height will be r minus 4r/3 pi. And on the top it will be h. So this f1 ka horizontal component, f1x, will be p naught plus rho g h plus r minus 4r/3 pi into pi r square by 2. Remember starting में I taught you for half disk. Half disk का result आएगा f1x. Similarly, the lower half also will be, take the center of mass. So this will be 4r/3 pi. So f2x will be p naught plus rho g, height is h, plus r, plus 4r/3 pi into pi r square by 2. If you add them, you'll get the same answer. 4r/3 pi will cancel. This will give you the horizontal components. Vertical component कैसा आएगा? We still need to find f1y and f2y. Actually, if you find one of them, you'll get the other one. Have a look at this. It's a good one. Meaning you can see how we are playing around with FBDs, forces, components, pressure, all that stuff. Now, did you guys do the homework question? If you have done that, you would have got an idea. I think Arjun did it. There's a very good way to do this. This question now, see. One is integration, okay? That brute force you can do this and you'll get it. The other way to do this is the logic, see. So meaning liquid is exactly till the top, na? Did I give R or 2R? 2R I gave, okay. Okay, now I understood why did I get 2R. Arjun, your solution is right. Now see, this is the logic what I'm saying. Forget about the hemisphere. Just look at the water on top of the hemisphere. Isn't that a cylinder? So if I draw the FBD of this water, above hemisphere, isn't it at rest? It is at rest. So this weight mg is being balanced by this force. Does that make sense? Isn't that the same force as this force? Whatever force liquids exerts on the hemisphere also will exert the same force on the liquid upward. Therefore, this force is nothing but that weight of that liquid. The weight of that liquid is, this cylinder ka height is 2r, the radius is r, density of the liquid pi r square, the radius into the height 2r minus 2 by 3 pi r cube into g. हाँ, प्रेशर भी होगा तो प्लस पी नॉट इंटू एरिया. Is that making sense? So you can actually generalize this. No matter what kind of curved surface I give you, let me give you any weird surface. Getting it? The force exerted on this upper curve is nothing but the weight of the liquid above the upper curve. So whatever force you exert on this, the same force the liquid also will exert. So this force, this mg is equal to this vertical force F. Fi on curved surface is weight of the liquid above the surface. Is that making sense? Now you could have done this with integration. I'm sure you might have got the same answer. Arjun, did you get the same thing?
I think I made a calculation mistake somewhere.
देख लेना. But logic समझ में आ रहा है ना? Without integration you could have done this.
Yeah.
Now how to use that logic here? Can I find F1 now for the upper half? So the weight of the liquid on top of this is nothing but F1 ka vertical component now. Is that making sense? Can you find? Try, I'll give you a minute. So F1 ko horizontal will come from pressure of center of mass into area. F1 vertical component will come from the weight of the liquid above that half cone. It's a good question based on pressures and stuff. By and force pressure, we are combining both and playing in this. If you look at this liquid actually, how do I draw this? The side B will look like this, na? So the liquid is there up to height h. So you need to find this weight. What kind of shape do you get here? This is like this, na? A triangle with a height h, isn't it? If you look at that piece, it's like a cake, I guess, a slice or something. It's like this piece, isn't it? Within this piece, you have that cone. How to find the volume of this piece? Volume of that thing will be area of the triangle. This is 2r and that is h half into base into height. That is area of the triangle into the height, which is h plus r. Does it make sense? This total height will be h plus r, right? Area of a triangle into height will give you the triangle of that sandwich kind of piece. Minus volume of the cone, which is half of 1 by 3 pi r square h. That is the volume of the liquid above the cone. This is area of triangle. This guy. This is the height. This is volume of half cone. So from here we will get F1 ka vertical component is density into this liquid. Let's just call this thing V. And what is F2y? F2y is nothing but F buoyant force plus F1y. From there you get F2y also. Clear with this? Everyone got what we did? Did you get how did I find the volume, right? Able to visualize this cake ka slice. So that half cone ka projection and then uska vertically have to take the water above that projection. So all that weight is balanced by this curved surface ka vertical component. This concept is making sense, right? Whatever force you exert on this cone should be the same force you're pushing it upward. And that vertical component should balance the weight. So there's no need to integrate for this kind of problems. That will save you a lot of time. Remember that concept. But it will give you only the vertical component. Clear with this? Take a break. Come back by 7:05. Any doubt so far, please ask me. It's a good question. They would ask you any two parts. I can ask you find the force due to F1. That itself will be a pretty good question.
So can you go to the previous page? Yes, okay.
Chalo, come back with 7.5. Yeah, next one. Right side of the cone is atmosphere. Yes. It doesn't matter. Anyway, the question is find the force due to liquid, no?
Sir,
Hmm.
if we find the force in liquid, then the pressure at the CM has to be of the liquid, right?
Pressure at the
CM, like the formula we are using, was like pressure
ये
at the CM
वेट का बोल रहे हो?
projected area. Yeah. नहीं सर, इससे
Okay.
पहले जब
प्रेशर भी ऐड
projected
करना
area,
है इसमें
इससे भी पहले.
है
Yeah, here I was asking that जब
लिया ना
pressure
पी नॉट
CM.
इंक्लूड किया ना
So sir, can you just show me like how like P naught दोनों साइड से cancel नहीं हो जाएगा या फिर something?
अरे गॉड क्वेश्चन पूछा फोर्स ड्यू टू लिक्विड नेट फोर्स क्यों कैलकुलेट कर रहे हो
Okay. Yeah, that's what I was actually trying to ask you. Like force due to बस liquid ही आएगा ना?
हाँ ये तो फोर्स ड्यू टू लिक्विड ही कैलकुलेट करना है नेट फोर्स क्यों कैलकुलेट कर रहे हो
हाँ, और
नेट फोर्स कैलकुलेट करेंगे तो पी नॉट का टर्म आएगा नहीं कहीं पे सब पी नॉट कैंसिल हो जाएगा
हाँ,
बिकॉज इट इज यूनिफॉर्म एवरीवेयर ना इट वोंट मैटर
yes.
ठीक है दैट वे लेट्स डू अ लिटिल इजी वन because in p naught what happens it lacks everywhere on the surface so it won't matter actually this is a question from HCV this is that gold crown that story get this 's an ornament weighing 36 grams in air weighs only 34 grams in water assuming some copper is mixed with gold to prepare the ornament find the amount of copper in it try I'll give you a minute 4.33 grams now see so mass is density of the mass is 36 grams fair enough so the 2 grams ka difference right buying force is 2 grams ka water weight So that is density of water into volume of the ornament into G. Let V be the volume of the ornament. So basically the ornament is ornament. Therefore, V is nothing but 2 cc, right? Because density of water is 1 gram per cc. Is that making sense? So the entire ornament ka value is 2 cubic centimeters. That is a buoyant force.
So 2
So-
gram of water weight would क्या? Oh,
What is buoyant force? Weight 2 gram क्यों reduce हुआ? Because of buoyant force ना? Right? 36 and 34. This reduced due to buoyant force. मतलब buoyant force is 2 grams का water weight, meaning it displaced 2 cubic centimeters of water. Let x cubic centimeters be copper. Therefore, mass will be density of copper into volume of copper, density of gold by volume of gold. Mass is 36 grams. Density of copper is 8.9 into x. Density of gold is 19.3 into 2 minus x. Simplify, you'll get x ka value from here. This guy will be 38.6. 9.4x is equal to 2.6. This is 1.04x. (26 by 104) or 1 by 4 cc. 0.25 cc. So the total ornamentica volume is 2 cc. In that 1/8 is copper. Clear? Got the idea? So the main idea is normally in air it is 36. Water may 34. What happened to the 2 grams? The buoyant force took it away. That means the buoyant force is 2 grams of water ka weight. That means it displaced 2 grams of water. So that is 2 cubic centimeters. So in that 2 cc, let x be copper. So 2 minus x is gold. So density into volume will give you the mass 36 grams. Clear, everyone? Easy one. So this is how actually Archimedes figured out that the weight of the displaced liquid and all that stuff came later on, but this is the main thing. And you know how Archimedes died? Finally, one day there was a battle. Some soldiers entered the city, right? And they were evacuating everyone and they're throwing out. This Archimedes was sitting in some library or somewhere and he was doing his work. The Greek, that I don't know who is Greek soldier or some soldier, came and said, get out from here. And this guy looked at him and said, get lost, I'm busy. The soldier got pissed off, took a knife, killed him, and went away from there. So later on, the general came to know about this and he felt regretted for not being able to use, he wanted to recruit him as his own military scientist. But the soldier got pissed off and killed him. So happens. Next one. Let's say we have a hinge here. We have a rod. Density of the liquid is 2 rho. Density of the rod is rho. Length is L. This is theta. Length of the rod is L. This is hinge here. So the lower part of the rod is hinged at the bottom of this thing so that it can't go outside. Find theta in equilibrium. since the density is less, it wants to come out. But because there is a hinge, it can't come out. So it will make an angle and it will remain at rest. Density of the liquid is 2 rho. Find theta. Get it, this is an easy one. $45. Yeah, Adrit. Try others. We have one answer already. It's an easy one. Romer, you have to draw the bind force at the center mass of the displaced liquid. Let's see. Yeah, 45. Right, Abhi. Right, Abhinav. See the FBD. So let X part be inside. The bind force will act upward here, FB, at a distance of X by 2. Here is the weight will act mg here at a distance of L by 2. Hinge reaction though will be there anyways. FB will be density of the liquid, which is 2 rho. Area of cross section, let's take it as A, it is not given, A into X into G. This will be rho A L G. So we have FB here, extend the force. This is theta. So this would be the perpendicular distance, which is X by 2 sine theta. This is mg. This perpendicular distance will be L by 2 sine theta. Basically, torque is balanced. Torque about the hinge is 0. So FB into the perpendicular distance X by 2 sine theta should balance mg ka torque L by 2 sine theta. This will be 2 rho A X G. X by 2 sine theta will cancel off. This is a rho A L G into L. Sine theta by 2 cancels off. So we get X square So you gave this is L by 2, this is theta, and this is x is L by root 2. Theta is 45 degrees. Check. Clear? Clear, everyone? So if they talk about this thing, so be careful. You have to apply the bind force at the displaced liquid. Next one. Next one is a good one. We have a liquid here. Let's say density is 2 rho. We have a cylinder. Density rho. Height of the cylinder is h. It is also height h above the liquid. Area is a. So cylinder is dropped. Is released from height h as shown. Find the speed when the cylinder has completely entered the water. And the cylinder just enters. Just when it completely goes underwater. It should have gone completely inside. Then what is the speed? Let's do one thing. Rho liquid, take it as 3 rho. Find max depth that goes inside. Let's see whether this will work or not. Take it as 2 rho only. 3 rho, I'm little worried. Because if the density of the liquid is too much, what can happen? There is a possibility it won't go completely inside, na? We need to check for that case also, but 2 rho, I think it should go. Let's see what is the catch in this question. Gravity is there. And assume there is no other resistances. Meaning there's no friction, nothing. So there's no loss of energy as such. There's only bind force and mg. Try. This question, right, later on we'll see in SHM, oscillations. They'll ask you find the time taken for it to completely enter the water. Or find the time taken for it to come back to the initial position. That would be a proper advanced question that is based on oscillations. But for that, this is the starting point there. So we will see this again in oscillations again. But for now, let's get the speed when it enters and maximum depth. Try, I'll give it 2 minutes for the speed. is the catch. Anyone figured out what's happening? There are two parts to the problem. So first, you're falling from here to this case. So this is not a problem because acceleration is constant. So when you're falling from here to here, acceleration is g. You must have got some speed also, v1. I'm not asking you v1. Then the problem starts from here. Once this guy starts entering, the buoyancy force is only due to this part. Buoyancy force is changing continuously. You get a variable acceleration. So you can't use the regular kinematics equations. You have to integrate. And then finally it got immersed. So at this point, the speed is v2. I'm asking you v2. And if you continue with the problem, it won't stop here. This will completely go inside here. And then it will come to rest. So it must have gone some more depth of y. This is what I'm asking. And then it will start coming out again. Why? The buoyancy force is more than weight, right? Because the liquid density is more, the buoyant force is more, it will push it out again. Is the scenario clear? This is what I keep telling you. Before solving the question, you should have an idea like what the hell is happening with the whole thing. What is happening? What is going? So here to here, it is constant acceleration. Here to here, it is constant acceleration. The problem is while entering. You getting the difference? Once you're completely inside, acceleration is constant. Once you're completely outside, acceleration is constant. But when the cylinder is entering, the buoyancy force is changing, acceleration is variable. So you need to find that y and v2. Now try. I'll give you a minute again to find v2. First, you can find v1. That is the easiest one. This height is h. This u is 0. So acceleration is constant. v1 square minus u square is 2as minus g minus h root 2gh. So this is the speed when the cylinder touches the water surface. Now this guy ka acceleration would be like this. So mg minus fb is equal to ma. mg will be rho a hg minus buoyant force will be 2 rho a xg is equal to ma. M is rho a hg. So from here we get acceleration. Rho a will cancel everywhere. C minus 2x by h into g. This is the acceleration. This you can write it as v dv by dx. Integrate. So how much x should it go? It will go to the total depth h. So 0 to h, 0 to h. The speed will go from v1 to v2. Agreed? The speed will vary from v1 to v2. No? You're entering v1 once you've completely entered v2. You get v2 square minus v1 square. This will be gh minus g to g. That will be h square by 2. G gets cancelled. Getting 0, okay?
sir, 0.
Means I'm getting v2 is equal to v1. So when it has entered also, the speed is luckily the same, root 2gh only.
So, sir, it has something to do with the density.
हाँ, basically क्या होगा ना, when it is entering, till some time it is accelerating, and after some remaining after it is decelerating. देखो ना, when the cylinder is entered exactly half, क्या होगा? Buoyancy force and mg will balance ना.
Hmm.
When the cylinder is exactly entered half cylinder inside, buoyancy force and mg cancel हो गया, मतलब ये zero हो गया. So after that half point, it started decelerating. Yeah, V2 minus V1 square by 2, that is. If I had given 3 rho na, cylinder, it wouldn't have gone only completely inside. It would have come out before only.
Sure.
You're getting it? क्या हो रहा है यहाँ पे exactly? So V2 is equal to V1 here. Means after it is completely entered also, speed is coming root 2 gh only. Please have a look at the steps. You can use work energy theorem, that also works. You must have messed up the calculations then. You have to integrate work done by buoyancy force. You can't take buoyant force into mg, into displacement. Force is not constant. That is the reason you didn't get a 2, I guess. Did you integrate work done by buoyant force?
I use work energy. First I found the potential energy there.
But buoyant force का work done कौन लेगा?
I found that work by integration. F dx,
Okay.
integral f dx.
And then?
F is 2 rho axg into dx
Uh,
0 to h.
That
will come mg.
Potential energy mgh, वो दोनों cancel हो जाएगा.
It will be 3 mgh by 2, right?
Why 3 mgh by
Center
2?
of mass is at 3h by 2.
God, think carefully. You are conserving energy from when to when? From this position to this position. H only ना, it traveled. 3h by 2 कहाँ पे travel किया? Center of mass. No. You're doing it from here to here. Everyone got the steps what we did? You could have used work energy theorem also. That also would have worked. Then how to get y part? Now you have completely gone inside. You won't get such a bad answer. The bind force has become 2 rho A H G. Mg is rho A H G. So acceleration will be upward. If you see, you'll get A is equal to G now. So finally the cylinder will travel till here and stop. So V square minus U square is 2s. Acceleration is constant. I can use 0 square minus V2 square is equal to 2 into, acceleration is upward now, G into minus y. This will be nothing but 2gh only. It will also got depth h inside. Because the numbers are rho into rho, it is coming out like this. If I had given 3 rho by 2 or something like that, it would have been more fun. Maybe I should have taken this block cut density is 2 rho and the liquid cut density is 5 rho. Then the numbers would have been little quite weird. But everyone got the process right. You can't do this problem directly. You have to do it in the air, then while entering water, then after entering water. There are 3 parts to the problem. Got this? You know what will be a good question? I can ask you, if they ask you to plot acceleration versus time graph. If they ask you to plot A versus T graph, it would look kind of like this. So initially it is falling down, minus G. Then once it starts entering the water, it linearly becomes 0. Then increase, then become constant like this to plus G. So this is the region where it is entering the water. This is the entering liquid. This is inside liquid. Acceleration has become positive up. This is in air. Making sense how the acceleration changes? At this point, right, buoyancy force and mg both became equal. Clear with that? I could have asked you an AT graph. Meaning, if I draw the full graph till it comes out, that will be more fun actually. So it starts here, constant, then it increases, then it is inside the water, then it starts coming out, then again it would decrease. The graph repeats. So this is the region when it is entering water. This is in air. This is inside liquid. This is the region when it is leaving the liquid, it is coming out again. This is again in air. And you come back to this position and the graph will repeat again from here. Making sense? This would be an acceleration time graph. I didn't ask you, but it could be asked. Clear with this? Now finding these times will be more fun. That we will see in oscillations. Right now we don't have that knowledge to do. Any doubts on 26? Clear with this? Can you tell me what is the problem? The same thing, if I had given a sphere, can you tell me what are the issue that we have while solving the problem? If it was a solid sphere which is falling inside, इसमें क्या issue आएगा? When it is entering the liquid,
Volume.
this volume will be messed up, na? It is not a uniform area. यहाँ पे देखो simply हमने rho AX कर रहे हैं. But if it is a solid sphere entering, it will be pretty messed up actually. The volume is changing continuously. It becomes complex to solve. Area varies. So we can do that, but it becomes mathematically complex. Next one. Let's see a more easy one. So we have some water here. We have an ice cube. Let's say Seidel, and a density of ice is 0.9 gram per cc. So this is some water. So case one, it is regular water whose density is 1 gram per cc. Case two, it is a salt water. Maybe someone added some salt. So density is slightly higher, 1.05 gram per cc. Case three, someone mixed up maybe some alcohol in this. It's a mixture of alcohol plus water. And density became 0.95 gram per cc, slightly less. Now, if the ice cube completely melts, what happens to the liquid level? Increase, decrease, remain same. Question is clear? You got an ice cube floating inside a water. There are three types of water: regular water, salt water, and alcohol plus water. Now, if the ice cube melts, what will happen to the liquid ka height? Increase, decrease, remain same. Yeah, case one remains same. That's a standard question. See, first of all, when this ice cube is inside, so how much is inside the water? So Romer, just may calculate x ka value, rho body by rho liquid into L. This comes out to be 0.9 L. That means this ice cube, this is 0.9 L, this is L, and this is L. So this volume of the cavity is almost 0.9 L cube. So basically 90%. So volume occupied or volume displaced is 0.9 L cube. Fair enough. Now, if you take this full ice and if you make it water, what remains same is the mass. Mass of ice will be mass of water. So mass of ice is density of ice into volume of ice is density of water into volume of water. This is 0.9 L cube is equal to density of water is 1 into V water. So water is also 0.9 L cube. So that means whenever this ice melts, it will generate how much water? 0.9 L cube. Fair enough. Now look at the cases. In case one, the density of water is 1 gram per cc. So this cavity which you have will be exactly 0.9 L cube. So if you take 0.9 L cube water and you put it in this cavity, the height will remain same. So this is the case, density of water is 1 gram per cc. Now case 2, tell me if you put salt water, density is more, so will it sink more or will it sink less? You can see from here, it will be less, isn't it? It will sink less. That means this cavity which we have, this will be less than 0.9 L cube. But if you take this water here, 0.9 L cube, and dump it in this will overflow. So this will increase. Is that making sense? Now, if you put this thing in an alcohol thing, this cavity, it will sink more. This is more than 0.9 L cube. It has to displace more water. And now if you try to put this in this will decrease. Density of salt water is more, so it should sink. What you're talking? So if I take you and put you in a more denser liquid, you will sink more or you'll sink less? You will sink less, isn't it? Yeah. So means the cavity will be smaller. All got this? Easy? More of an intuitive thing? Any doubts on this? So the first part is a standard question. The other two are little variations of this. Yeah, the liquid water. There are 3 cases, na God. Clear, na? Utsa, Vartika, got this? Malika, clear? Swastika, got this? Udayan? Neil? Last one for the day. We have a container here filled with liquid. Inside there is a wooden plank. Floating wooden plank. On top of this wooden plank, there is a block. Case 1, density of the block is greater than density of the liquid. Case 2, density of the block is than the density of the liquid. Liquid, water, whatever you want to call. Liquid density is rho L. So this is height h, the height of the liquid. This which is sunk inside, this is small h. Now what you did, you pushed this block into the liquid. If the block is thrown into the liquid, what happens to capital H and small h? Increase, decrease, remain same. Both the cases. Capital H is the height of the liquid. Small h is the depth of the wooden plank inside the liquid. Let's do for the first case and then second case we'll see. So density of the block, meaning question is, you're in a ship, in a boat, in a swimming pool. You have a metal block. Density of the block is greater than liquid. You took the block and threw it out. What will happen to the water level? What will happen to your boat? In the second case, you have a thermocol with you in the boat. You took the thermocol and threw it into the water. It is lighter than the liquid. Now what will happen to the water level and what will happen to the boat level? Question is clear? Two scenarios. One case, you're dropping a metal block, which is heavier. Second case, you're dropping a thermocol block. Something of that sort. How do we do this? Think. H increases, capital H decreases, small h decreases, capital H increases. Let's try to take with an example, okay? That will make things much better. Let's see the case 1. Let's say density of the block is 10 times density of the liquid. Example. You could have taken anything. I'm just taking 10 times. Now, before starting the question, now let's take like this. So let's say you take an empty plank, okay? Empty plank. There is no block, nothing is there. This is your small h. Now, place the block. Question is not started yet. Now, if you place the block, what will happen to the depth? Increase or decrease? Think of like this. You're in a boat,
Decrease.
and if you go and sit on it, what will happen? Suddenly the depth will increase. So basically, h increases. So you went and kept the block on top of it. Question starts from now, isn't it? Now, if you throw it back, what happens? The boat will come out again, isn't it? So basically, small h will always decrease, isn't it? Now, in this process, see what happens. The moment you put the block, how much water did you displace? In order to keep this thing floating, remember density of the block is 10 times rho L. The boat displaces. This boat will go down. H increases. And this water level, right, will rise. Rises by 10 times the volume of the block. Do you agree? Why 10 times? Because density is 10 times now. In order to keep it floating, you need to displace the same amount of weight. In case you're wondering how we got this, F buoyant force should be equal to mg. So density of liquid into volume of liquid into g is equal to density of body into volume of body into g. The volume of liquid will be 10 times volume of body. Because I took 10 as a number, you could have taken anything. Is everyone clear with this? Now, Udayan? Udayan, are you there? Focus. Clear? Ali? Anika? So if you put a 10 times the density ka block, you need to displace 10 times the water in order to keep it floating. It's not that clear, everyone. Now question starts from here. Now you took this block and throwed it back. What will happen to H? So this block has fallen inside this. It will come back to original position. H decreases and comes back to initial position. And also you displaced how much water initially? This volume was rising 10 times V na? So this water level will go back 10 times V inside. But this block which you pushed inside also will displace 1V. You're getting it? Water level will drop by 10V. And the block displaces 1V. Therefore, there is a net minus 9V ka deficit. So what will happen to the water level? Therefore, small h and capital H both will decrease. Meaning, I'm just showing with numbers, but logically you think about this. So again, when you put a heavy object on the boat has to sink a lot in order to keep this floating. Agreed? When you took that block and throw it back into the water, now there is no need for you to make it float. The boat will just come back to the initial position and all the displaced water will come back to normal. Is that making sense? You can try this at home. Today, now what you do, in the bathroom, right? The bucket of water is there. Take this mug, invert it, put it in reverse with air and all, and then try to push it inside. What happens to the water level? It rises now. If you push it out, what will happen? It again, water level goes back to the normal. Is this thing clear? So when a heavy object is dropped into the water level will decrease, the small h also will decrease. But that is too small, Anika. This thing is decreasing 10V, this is increasing only V, na? That is a catch, isn't it? All got this? No, the numbers, why it is important? Because of the next one. So say, Anika, the logic is this. In order for the block to float, you need to displace how much? 10 times volume. But if you throw the block into the water, it can displace only 1 times volume. Meaning remaining 9 times volume will decrease, isn't it? And now in case 2, let's say density of the block is, again, example, half of density of liquid. Therefore, block we need to displace V by 2 to float. This is where the interesting thing happens. So if you keep the block on top of this, the liquid level will rise by how much? V by 2. Agreed? Now, if the block is dropped inside, what will happen to the block? Will it sink? It will not sink, na? The block also will float. The block will not completely sink. Then what will happen? Because you throwed it back, the volume will go down by V by 2, but the block also will displace V by 2. The meaning is, if you take a thermocol, you put it in your boat or you put it in the water, it is not going to get affected, isn't it? So the water level remains same. H remains same, but the small h will always decrease. Are you getting the catch? Again, I'll explain the whole thing. Listen. When you have a heavy object, it cannot float by itself. Agreed with the statement? So when you put this in a boat, the boat has to displace more water in order to float this heavy object. Therefore, when you take this heavy object and put it in a boat, the water level will rise more, let's say 10 times. And when you throw this block back into the water, the 10 times what it increased will come down, the water level decreases. Ye clear hai? But now, if you take something like a wood or thermocol, if you put it in a boat, again, the boat has to displace, isn't it? If you put it in a boat has to displace water. But if you take the thermocol and throw it into the water, thermocol also can displace the same amount of water. Means if you put the thermocol in the boat or in the water, the displaced water is only V by 2. But if you put a heavy object, the problem is you will displace 10V, but you'll get only V back from the block. Are you getting the difference? If the block can float by itself, it doesn't matter where you keep it. So you're getting the point? If you can float by yourself, how much will you displace V by 2 now? If I put you on the boat, how much will you displace V by 2? But if you can't float by yourself, and if I put you in the water, how much will you displace V? But if I put you on a boat, you'll displace 10V. Are you getting the difference? So we can write this as a generalized statement. If the block can float by itself, it doesn't matter where you place it. It displaces the same water whether it is inside the boat or in the liquid. Think about this. You're still confused. We can discuss this. It's more of a theoretical question, whether in blank or in liquid. The main idea is when you're floating, you really don't displace V. You displace always less than V. So that amount you also can displace on your own. But if you're very dense, you can't displace so much liquid to float, then you're taking the help of a boat. The boat will displace much more liquid than you can displace on your own. Is that making sense? Okay. So think about this. We have done almost 28 problems. So with this, the fluid statics ka part is done. So next class when we meet, right, we're going to start with fluid dynamics. Liquid will start flowing now. That's actually a little easier part, but yeah, in that also we have some good questions. So mostly next week we will wrap up this fluid dynamics also. So okay, with that we'll wrap up for that day. Right. So do go through the notes. I did send the heat and thermo ka sheet, so you can try that. The questions are pretty good in that.